Awesome. Okay, so we're going to jump back into where we left off last Thursday. So if you remember, we were trying to draw samples from the distribution over failures. And we said that we knew we couldn't compute the normalized density of the failure distribution, but we could compute the unnormalized density by computing that numerator. And so we were talking about different ways to then draw samples from this unnormalized density so we could kind of represent this distribution implicitly with our samples. And so we talked about rejection sampling and we talked about Markov chain Monte Carlo. And we left off talking about Markov chain Monte Carlo and kind of some of the challenges that we might end up with when doing Markov chain Monte Carlo. And one of these challenges was that kind of everything works with Monte Carlo in the limit of infinite samples. So in the limit of infinite samples, Markov chain Monte Carlo will give us distribution samples from the failure distribution. But we were saying we don't have time for this, and so we need to figure out what to do in practice when we're always going to have some finite set of samples. And so we talked about some different tricks to do. One was kind of adding this burn-in period, which people sometimes do to just throw out the first few samples. There was also this thing called thinning, where because these samples the next sample depends on the previous sample, the samples are actually correlated within the chain. So to get these kind of uncorrelated samples, people will often do this thing called thinning, where they keep every like 5th sample, 10th sample, something like that. And then the last thing we were talking about was this idea called smoothing. So that's what we're going to kind of dive deeply into for the first part of today. And we had this Pluto notebook where we were looking at, where essentially the idea was that we had now this bimodal failure distribution. And we saw that when we just tried to do kind of this naive Markov chain Monte Carlo to sample from this bimodal distribution, we only got samples from whichever failure mode we started in. And the reason for that was because we had this proposal, or not proposal, but this kind of distribution we were using to propose the next sample. And when it was called a kernel, when we were using this distribution, we saw that it assigned very low likelihood, no matter what we did, to kind of points in this failure mode over on the other side. And so it was very unlikely that we would make that big jump and actually switch over to a failure mode. So in the limit of infinite samples, this would eventually happen. But because we're taking a finite sample, a lot of times our finite sample is just going to contain samples from this failure mode. So we said, let's try to help this algorithm move between these failure modes by kind of smoothing out the failure distribution. And so the way we said to do this was we'll define this distance function that we call delta. And we're just saying that this function should return 0 if the trajectory is a failure, and it should be positive otherwise. So it kind of represents a trajectory's distance to failure. And one really easy way to do this is to just take the max of the robustness and 0. So the robustness will be positive when it's not a failure, and then we'll make sure it's 0 when it is a failure. So then we said what we could do is we could just rewrite our unnormalized density for the failure distribution. And instead of saying tau not in psi, we can just use this condition, which means the same thing, which is that delta tau is equal to 0. And so we said, okay, now what we can do is we can say that this indicator function is actually kind of similar to a normal distribution with a very small variance. So here we had, we have this indicator function, it's 1 at 0 when delta tau is 0, and it's 0 everywhere else. And we can kind of approximate that with a kind of this smooth approximation, which is a normal distribution centered at 0 with this kind of small variance. So what we could do is we could just take our indicator function in our unnormalized density and replace it with this kind of smooth approximation. And the idea is now we'll assign non-zero probabilities to success trajectories with higher probability for successes that are closer to failure. And what's kind of cool is we could actually now take this epsilon parameter, which is the variance of that normal distribution we replace it with, and use it to control kind of how much we're smoothing out this distribution. So when epsilon is 0, that means that there's no smoothing, so the variance is 0 or just kind of collapses back to this. And then you can imagine when epsilon is infinity, if you imagine kind of an infinite variance for a normal distribution, it's like infinitely wide, it basically just becomes kind of uniform. And so this is kind of uniform now, and then our unnormalized density just becomes the failure, the nominal trajectory distribution. And so when epsilon is infinity, it approaches the nominal trajectory distribution. Okay, is there any questions up to that point? Yeah.
this is more of a. Can you say this again?
Sure.
Can you say a little bit more about why we're modulating p-bar to be that? Like, why is this the probability?
Why we make this equation?
No, the one above.
This equation?
Yes.
This is just the unnormalized density of the failure distribution.
Right, but how do we get to that to the next one?
To this one? We just said we defined this distance function in some way. Common way to do it is max robustness in 0, such that if that distance is 0, tau is a failure. And if it's not, then it'll be positive, or it'll be a success. And then basically we can just say then the condition that tau is a failure is the same as the condition that that distance function evaluates to 0. So we just replace this.
Okay.
Yeah. What other questions do you have on that? Yeah.
So the smoothing just lets us kind of like expand this distribution more. So then, like, I guess now since our distribution is like larger in a sense, is it possible that like there's trajectories that aren't as likely?
Kind of, yeah, and more specifically, we're now going to have a bunch of samples that are not failures because we just assigned some non-zero probability to samples that are not failures, and our failure distribution should only consist of failures because it's the distribution over failures. But we can actually solve this problem in that we can just reject all of the samples that are not failures, don't include them in our final set of samples, and we'll actually be left still with samples from the failure distribution. So this may seem kind of intuitive, but it's not necessarily an obvious result to derive. But one way you can think of this, and actually what this is completely equivalent to, is doing rejection sampling, which is what we did at the beginning of lecture last week, with our smooth distribution as the proposal distribution. And then we just reject all the ones that aren't failures, and then the ones that are left will be from the failure distribution. So let me show you guys what this looks like. So here we have similar plots to what we saw last week, where we're trying to now sample from this kind of bimodal failure distribution. And the plot on the top here, in red, we show the true failure distribution that we're trying to sample from. And then in this purple line is the smoothed version with epsilon equal to 0.05. So we have kind of just this tiny bit of smoothing that like smooths out this edge here, such that now we have some non-zero probability out here, and then this is still some really small non-zero probability. Here we're showing the chain of samples, so even still with this small amount of smoothing, we didn't manage to jump over into this other failure mode. But then what we do is we just do rejection sampling, so that's what this part is showing on all of those samples, get rid of all the ones that were not failures, and then we're left with samples from the failure distribution, but we still have this issue where we never jumped over to the other mode. And so all we really need to do is like, we smooth it out a tiny bit, but this is still a really big jump for it to have to make. And so what we can do is try to kind of smooth it out a little more, so let's increase that parameter a bunch. And now we can see kind of this nice, big, smooth distribution, and we can see ourselves kind of jumping back and forth between these failure modes. And kind of and now we have, nice samples from both sides here. The one drawback is we're now sampling some non-failures, so we're kind of wasting some of our samples on samples that we're ultimately going to reject, but we needed those to be able to kind of efficiently explore the full space of possible failure modes. Yeah, and so if we have somewhere in between, I think I want to show you guys this too. Maybe this one. Yeah, so we have something somewhat in between where we're almost jumping back and forth enough, but we don't jump back and forth quite enough for our limited sample size. Sometimes we can get a few samples from our other failure mode, but not enough to fully even it out. So this is really just a parameter that you kind of have to play around with for your system. Yeah.
So right now you're not plotting the next step proposal, the kernel or whatever it's called, right? It's not visualized. So could you also, instead of doing that, just widen your kernel distribution, and then it would also manage to kind of jump over at some point?
Yeah, good question. So the question was, could you just widen your kernel distribution and then it's more likely to jump back and forth? You could do that. I think in general, it won't be as obvious, like what kernel is going to allow you to jump back and forth. Like imagine, this is one dimensional, but imagine you have like hundreds of dimensions. It's not super obvious how to just like design a kernel that's going to do that for you. And then also you might not want to make your kernel too big because it might like decrease performance in other ways.
Okay. And thank you. And then another question. Now let's say this is what I have in my experiment is this. Is there in general an easy way that I can tell that I actually haven't found a good epsilon yet and I should keep looking? Because maybe this is what I measure and I'm like, oh, I guess nice, I found 2 different areas and I've modeled them and then I'm just going to call it a day. Can you like look at this and be like, oh, obviously I didn't do a good job yet?
Yeah, that's a good question. So the question was like, how do we know if we found a good epsilon if we don't know what the failure distribution actually looks like? Okay, so I'll give you 2 answers. The one answer when we do research papers is we'll run this for just a super long time on like the naive rejection sampling thing. Like I think I've run experiments for like 30 days on a computer to get a baseline. And then you show that your thing does it better in like 3 hours or whatever. And then you need to like, in the real world, you're just gonna have to trust that your thing is kind of working. I think in general, though, if you have more domain knowledge about your system, then you could understand if it seems to be missing things. I don't know. Is there anything else that you could do? Yeah. Okay. Any other questions on this? Okay. Let's go back here. Yep.
Sorry if I missed this, but can you describe at high level what's the difference, sort of, not at infinity, but at a certain fixed amount of time, what's the difference between something like rejection sampling versus Markov chain monocoloring? Because both are p-weighted now, right? Both are now weighted. The distribution, the proposal distribution we give for in rejection sampling is also ideally weighted by what you guess at the failure distribution is. In a sense, like, does it perform better anytime? Does it, like, what?
I think, so the question is kind of like, what is the difference between this limited finite sample Monte Carlo and what is rejection sampling? And, well, there's like a few differences. I mean, one, like in rejection sampling, your samples are not correlated with each other. We're not trying to build out this kind of big chain, which is why I said to be kind of careful trying to draw the parallels there. And then also I think can be really tough with rejection sampling is you have to come up with that proposal that like completely bounds your distribution. You have to pick that value C that like gets that height up, and it's generally just very difficult to do. And with Markov chain Monte Carlo, you don't have to do those kinds of things. So that's, yeah, this is typically used more often. Yeah. Yep.
Do you still have those challenges when you run rejection sampling on the smoothing markup?
Yeah, the good question. So the question was, do you still have this challenge? Because now we're doing like rejection sampling again right here. No, because you know that the smooth density like exactly matches your failure distribution in places where your failure distribution has non-zero probability, and it kind of lies above the failure distribution in places where it has 0 probability. So you already know that it's like overbounding your failure distribution, so you don't have to worry about, like, you can set C equal to 1 and you're perfectly fine. Okay. Cool, okay, and so then the last thing to kind of wrap up the failure distribution is just a few quick tips for scaling things up. So yeah, I wouldn't be showing you these methods if it wasn't possible to apply them to more than just a one-dimensional Gaussian distribution. And we can in fact scale them up to these very high-dimensional problems. So for example, the pendulum we know is like around 50-dimensional, and we can still scale it up to draw samples from the failure distribution of the pendulum. So I'd recommend checking out these example problems in the book if you want to see like exactly how all the code works. But just to prove to you that it does work, I'll show it to you real quick. So here's actually trying to sample from the failure distribution of the pendulum. And you can see that we've applied some smoothing here. So in the smooth distribution, we get some samples that are not failures. And then here we can reject those and get samples from the failure distribution. And so what's going on here is like these samples, they're not just like 1D points anymore. These samples are full trajectories. So they're samples of the initial state and all of the disturbances for those trajectories. And so like every time we propose a new one, we propose an entire new trajectory and decide whether to accept or reject it. And then also you might see like this looks a little off balance. It's probably like equally likely that the pendulum falls to the right and falls to the left. And so kind of similar to up here where we had this issue where it wasn't flipping around enough, maybe what we should do is like increase our smoothing parameter a little bit. It takes a minute to run because this is a bit of a bigger problem, but we should see that this will kind of balance out more if we smooth it a little more. So yeah, so we get a few more non-failure trajectories, but we're able to get kind of this nice representation of the distribution over failures for the pendulum. And you guys can check out the code for doing that. It's all in the notebook. So if you download the notebook, you're welcome to look through it. I'll be honest, the code for the notebooks I show in class is not the prettiest because I've been making them quite quickly before lecture, but you're welcome to check out any of the code. Okay, so that's one thing. Smoothing helps quite a bit to kind of sample from these failure distributions that have multiple failure modes that are very complex. There's a lot of other things that help. There's like you probably take a whole class on Markov chain Monte Carlo. One thing that really tends to help is to use gradients of the likelihood to define the kernel. So we were just defining this kind of naive Gaussian kernel. It basically makes it so we do kind of a random walk through the space that we could be sampling. But in general, we know that we're going to end up wanting to sample from like high likelihood regions more often than we want to sample from low likelihood regions. And so there's these methods that end up using gradients and a lot of inspiration from physical systems to kind of random walk, but in a nice direction, kind of towards increasing likelihood. And then every once in a while, you'll decrease. And you can kind of use the gradient to guide that walk. So if you're interested in like more specifics on how that works, we talk about it in section 3.6.3.3. There's also one that's very famous called Hamiltonian Monte Carlo, or HMC, you may have heard of. And then kind of the state-of-the-art one that a lot of people use these days is NUTS, or the No U-Turn Sampler, kind of a funny name. And so yeah, these are all things that you could use to make your MCMC a bit more efficient. And then secondly, another thing that can help scale things up is more of just a paradigm, which is probabilistic programming. So we actually talked about this a little bit when we were doing parameter estimation. But it basically allows us to specify probabilistic models as computer programs, and then the computer probabilistic programming language can kind of understand that and perform this inference automatically for us. And so so yeah, both of these are advanced topics, won't be on the quiz, but they're super interesting if you want to get further down this path. And I just want to show you real quick with probabilistic programming, because it's like so cool. Basically, we have this algorithm in the book for it, and all of this will look probably very familiar. So we say sample failures, and we make this model for a probabilistic programming language called Turing.jl. And basically it requires you make this model function. So we just modeled the rollout of the system, which is the way that we draw a sample from our system. And we basically say like, S is sampled from the initial state distribution, and each of our disturbances are sampled from the disturbance distribution. And then we just tell it that the density of the distribution we want to sample from is kind of this like smoothed density for the failure distribution. And then Turing will just like sample from it for us, which is super cool. So I'm not expecting you to understand all of the syntax right here, but what I hope you take away is like, you can kind of very easily specify all of these things, and Turing will just like do the inference for you. So if you want to run Hamiltonian Monte Carlo or NUTS or whatever, Turing has implementations for all of those things, and it can draw samples from your failure distribution by just running this block of code, which is pretty cool. So yeah, super cool. Okay, that's it for this lecture. Are there any questions on that? Yes.
This is probably not the best question to ask when we're usually using Julia in the course. But are there similar things in Python as well that we could access?
For like the probabilistic programming, I think there's PyMC. Pyro. It's a cool name.
Stan. I think you can use Stan from Python. I think Stan is the
Stan?
I think that's the OG. But I think it's in C++, but you can use it from Python.
It's harder to integrate with Python, in my experience. Or it's harder to do this kind of stuff.
Of course.
Oh yeah, it looks like Stan asks you to define basically your prototypes in a giant string.
Okay, awesome. So that was failure distribution. So kind of going back through the sequence of things, we did we started our failure analysis with falsification. We were just trying to find any failures we could. You did that for project 1. Then we talked about how to sample from the full distribution over failures, which is a little bit harder. And now we're going to do something kind of one step further even and try to estimate the probability of failure. Okay, and part 1, we're going to do this also in Thursday's lecture. What is the probability of failure? So we're going to talk about what this means mathematically. Before I get into this lecture, I'm going to give kind of a similar caveat that I gave last lecture, which is like the methods I'm going to talk about today, I think they took me a few times through before they like fully clicked in my mind. And I think especially for a lot of these methods, there's like a lot of different angles you could kind of come at for understanding them, and they're all valid. So I'm going to try to present like as many different angles as I can today, but you know, maybe after this lecture, go check out the book, maybe come back to the lecture, and then I'm always happy to like explain a different way on Ed or through office hours if it's like not clicking in some way. But okay, so let's talk about probability of failure. So mathematically, the probability of failure is defined as this expectation, which is the expectation over trajectories from the nominal trajectory distribution, basically just whether or not they're a failure. So if you remember from, I think it was chapter 3, we were talking about metrics that are either 1 or 0, so this is either 1 or 0. If you take an expectation of them, you get a probability. And then furthermore, we can kind of just write out what this expectation is as an integral. And so we could say the probability of failure is kind of this integral over all possible trajectories of whether or not they're a failure, weighted by their likelihood under the nominal distribution. And this might look familiar to you, because you know, from the lecture that we were just talking about, you'll notice that it kind of matches exactly what we had in the denominator of the failure distribution. And so it turns out that the probability of failure is just the normalizing constant of the failure distribution. So there's kind of this connection here. And so it's kind of, you know, equal to this area under the unnormalized failure distribution density. And we just finished talking about how this normalizing constant is generally intractable to compute. Exactly, and that was why we had to go through that whole business of trying to sample from the failure distribution. And so in this lecture, we're going to talk about ways that we could actually go ahead and like go about estimating what that denominator is, or in other words, what the probability of failure is. Okay, so plan for today, we're going to discuss a few methods to do that, and then we're going to continue discussing them on Thursday. So we'll start with direct estimation, which we've already actually seen a couple times in this class. Then we'll go to an improvement on direct estimation, which is importance sampling. So this is like a super fundamental concept for this class. If you walk away with a few things, I hope that this is one of them. It's super useful and really cool. And then we'll talk about some extensions of importance sampling, starting with one called adaptive importance sampling. And that's it for today, but just another note. So I kind of gave you a hint last time when we got to fuzzing. I was like, this is what I would start with for project 1. Importance sampling is what I would start with for project 2. So actually, if you haven't checked out project 2 yet, no worries. But essentially, what we're going to do is just take all of the systems that we used in project 1 to find failures of, and we're going to try to estimate the probability of failure of those systems. And you'll need to beat the baseline of direct estimation, and one way to do that would be to use importance sampling, which we'll get into. Okay, but let's start with direct estimation. And let's imagine that we're just going to produce samples from kind of our nominal system. And I'm going to break it up into this 2-step process. So there's nothing crazy going on here. To produce a sample from our nominal system, we're just going to say we're going to perform a rollout of the system. So for example, maybe we perform a rollout of the inverted pendulum. And then the second step is we're just going to label the outcome as 1 if the trajectory is a failure, and 0 otherwise. So we just check whether or not it's a failure. And imagine we do that a whole bunch of times, and now we have this data set of basically 1s and 0s. And it turns out we could think of this process as equivalent to producing samples from a Bernoulli distribution, which is defined by the parameter pfail. So this all sounds really fancy, but all that's going on is I'm just saying, like, we have this parameter pfail, and every time we sample our system, we'll get a failure with probability pfail, and we'll get a not failure with probability 1 minus pfail. And that is just a Bernoulli distribution with that parameter. But the reason that I'm kind of going through the trouble of writing everything down like this is because we can actually then think of the problem as just a parameter estimation problem, which is what we were doing when we were doing the model building or the system modeling chapter in chapter 2. And so we could just use those same exact techniques that we were using in chapter 2 to actually go ahead and estimate the probability of failure. And specifically, the techniques we talked about for doing that were maximum likelihood estimation and Bayesian estimation. So we're going to see how we can do both of those, starting with the maximum likelihood estimator. So it turns out that the maximum likelihood estimator for a Bernoulli distribution, assuming we had kind of a data set of these values of whether or not it failed, given samples from our nominal distribution, is just exactly what you would think it would be. So it's probably, if I came up to you on the street and I was like, here's a bunch of data, tell me what you think the probability of failure is, this is probably what you would do. You would just basically take the number of failure trajectories and divide it by the total number of trajectories that I gave you. That's the maximum likelihood estimate. A bunch of p-fail hats, the expectation of that should be the true probability of failure. The next is consistency, which basically says an estimator is consistent if it converges to the true value in the limit of infinite samples. So in this case, we have like the limit of, as the number of samples m approaches infinity, of our estimate should equal the true probability of failure. And then finally, the variance is just a quantity that tells us kind of the spread of the estimates around the true value. So let me try to kind of clear all of this up with an image here. Oh man, I meant to cover these up and have you guess them. Well, all right, I guess we're just gonna go for it anyway. So this estimator over here, well, let's start by looking at that. So all these plots, the true probability of failure is kind of this dashed line that you see here. And so we see that the estimate, the mean of the estimate is kind of that dark line. And then imagine we ran a bunch of trials and like plotted the spread of all those estimates over those trials. That's what the kind of shaded region is. And then as we move to the right, this is like more samples that we gathered to create our estimate. So in this case, the estimate over here, it's not unbiased. So it actually is biased, because if we look at any point in time, kind of the expectation, which is that blue line of our estimate, is not the probability of failure. It's got kind of this bias to be above the true probability of failure. But it is consistent, because if we look kind of in the limit as we increase our amount of samples, it's converging to the true probability of failure. What's that? Why is it biased? So an estimate is unbiased if its expectation on expectation, it's equal to the probability of failure. If we look here, the expectation is kind of like this blue line. So its expectation, like look, for example, right at this point here, its expectation is actually above the true probability of failure. And so it's biased. Because it's only on one side. Yeah, that's exactly right. Okay, and then if we look over here, we kind of have the opposite thing going on. So the expectation, it actually does equal the probability of failure, but it's not really converging to the true probability. It's kind of just like the variance is staying wide for this whole time, and so it's actually not consistent. It doesn't converge to the true value in the limit of infinite samples. And then finally, this last one is both unbiased and consistent. You can see it's kind of symmetric around the probability of failure. That's another way to kind of look at bias. And it's converging. You can see the variance decreasing and decreasing and decreasing as we get more samples. And so it is consistent. And then also, just to illustrate variance, So we say the samples, or when we have like a small number of samples here, we have a high variance. So there's a lot of different estimates we might get if we only ran a few samples, for example. And then over here, if we run lots of samples, then we expect that we're going to get like a pretty good estimate that's near the probability of failure. So ideally, we have unbiased, consistent, and low variance. That's what we want, but we don't always get that. Any questions on these metrics? Yep.
Work better typically when you have more samples.
The question was, an estimator should always work better when you have more samples. That would be, I think, a desirable property. I mean, I would love my estimator to work perfectly with one sample, but I think in general, like that's a desirable property and a property we often observe. But it's not always true. Like you could end up with an estimator like this that like doesn't converge, and like no matter how many samples you give it, it doesn't get better. But that's not typically what we're looking for. Yeah.
So during post-training class, they say that Monte Carlo is like high variance but low bias. Would you agree with that?
That's a good question. So the question was, in reinforcement learning, they often say Monte Carlo is high variance but low bias. So we're going to see in a second, actually, that leads me to kind of the exact next slide, which is let's look at what these metrics are for this kind of Monte Carlo direct estimator. So it is unbiased. So we do expect it to, on expectation, give us the true probability of failure. And then specifically the variance of this estimator, we can actually calculate what it is. So we just take the variance of a Bernoulli distribution, divide it by the number of samples. And so one thing that we can now kind of analyze this equation here to understand a little bit more about the performance of this estimator. And so for example, what happens to the variance as m approaches infinity, as the number of samples we take approaches infinity? It goes to 0, yeah. And so that means that it's consistent because we're going to converge to the true value. We're going to have a variance of 0. We'll get exactly the true value in the limit of infinite samples. Yeah.
How do we know this is unbiased?
I didn't prove it for you, but you can prove that.
Can you give like a sketch in the sense of, I can see that it sort of makes sense, but I can't actually see how it would go about moving it. Like in the beginning, it's like it could be very wrong, and then it will get more consistent, which makes sense.
But I guess it's kind of equally likely to be very wrong in either direction. Okay. So on expectation, yeah, that's definitely not a proof, but that's some intuition. I think I have a little note that's like, you should make an exercise where they prove that this is true. So it might look out for the exercises, and I might have it in there, and you can give it a try. Yeah. Okay. Any other questions on that? Does that answer the question you're asking? Yeah. Good. Help you in this class, help you in other classes. You know, it's just the all-encompassing class.
That keeps on going.
Keeps on going. Any other questions on this? Okay. So that's one. Oh, okay. And then just to kind of show how we would do this empirically. So in general, we don't actually know the true probability of failure. What we could do to kind of understand the variance of an estimator is we could imagine that I just kind of did, well, this is exactly what I did. So I did 10 trials with 5,000 samples each. And then I kind of cut each trial off at some value as we go across. And so, for example, I say if I only had the first 1,000 samples of those 10 trials, what's my mean estimate of the probability of failure? And then what's kind of the spread of those 10 different estimates? So it does exactly what you would expect. As we get more samples, we get kind of a much smaller spread in those estimates. So that's how you can kind of evaluate these things empirically. Okay, so this is kind of one observation that we can make from this variance, which is that as the number of samples increases, the variance in the estimate will decrease. So this is kind of intuitive. It's like what we were saying, when we get more samples, we typically will get a better estimate of the probability of failure. And then the second thing that I want to observe here, though, is that as the probability of failure decreases, so we typically don't know what it is, but we might know kind of the order of magnitude of the probability of failure of the system that we're analyzing, the variance in the estimate increases. And so this is, again, kind of bad news for systems with rare failure events. And we're going to discuss important sampling techniques, as I mentioned, that will help us kind of address this issue. Okay, so before we get into importance sampling, let's talk about one more issue with maximum likelihood estimation. So we'll use a collision avoidance example. So you can imagine that we want to estimate the probability of failure for an aircraft collision avoidance system. And we have an aviation safety database that contains flight records from the month of December. And so then let's say that there were no recorded mid-air collisions in December. What would be the maximum likelihood estimate of the probability of failure? Yeah.
0.
0, yeah, exactly right. But we're pretty sure it's not 0. Actually, in fact, very unfortunately, we know from last week that it's not 0. And so we could use Bayesian estimation instead to kind of produce a distribution over the probability of failure. And so what we would do then is we'd say maybe it's 0, but we also have kind of this non-zero probability that the probability of failure is something else. Okay. So how do we do that? Well, remember these fun times where we were flipping frisbees? And so we're going to do basically exactly the same thing. So we, said we wanted to infer this distribution over the probability of the probability of failure given our data set. And when we were flipping frisbees, we said we flipped a whole bunch of frisbees to gather this data set, and we said our theta was the probability of both frisbees landing in the same direction. And then we said n was the number of times they landed in the same direction, m was the total number of flips, and we were able to find out that our posterior distribution over theta, so this p theta given d, followed this beta distribution. So all we're going to do is kind of reformat this for our probability of failure estimation, where we're going to say, instead of collecting a bunch of data by flipping frisbees, we're going to do a bunch of rollouts of our system. And so now our theta, instead of being the probability of the frisbees landing in the same direction, it's just going to be our probability of failure. N will be the number of failure trajectories we get in our rollouts. And then m will be the total number of trajectories that we simulate. Okay, so let's see how that looks. Okay, so we can see here we're simulating our inverted pendulum. And here I'm showing the maximum likelihood estimate. So we had 8 failures and 50 trajectories, so we get that the estimate's around 0.16, for example. But then, of course, we said if we have rare failures, this can be an issue. So now let's imagine, that we have kind of a very small perception noise, so failures become more rare. Now we don't observe any failures, and we're estimating that the probability of failure is 0. And so what we might do instead, then, is kind of take a Bayesian approach where now we're estimating a distribution over this probability of failure. So here's our distribution over the probability of failure. We see that, it's still likely that it could be 0, but there's some non-zero probability that's a little bit higher. The probability of failure is a little bit higher than 0. And you can imagine that, as we simulate more and more trajectories and we don't observe any failures, this distribution gets kind of sharper and sharper, which is kind of hard to see with the axes there, but it's basically getting sharper. And one thing that I think is really cool about Bayesian estimation is we can now kind of make extra claims about our system. So for example, I could say something like, what is the probability that the probability of failure is less than 0.01? So let's say we know, when we deploy our system, we want to be sure that the probability of failure is less than 1%. And so we could actually assign, what is the probability that that's the case by just looking at the probability mass that's to the left of 0.01 on our plot here. And specifically, that's equivalent to just calling the CDF, or cumulative distribution, function for our posterior. And so we can just call that function and we'll say the probability that's less than 0.01 is 0.637, for example. And what that looks like on the plot, if we kind of zoom in a little bit here, oops, it's a little too much. It's the probability mass that's to the left of 0.1 in our distribution. The other thing we could do is say, what value are we 95% confident that the probability of failure is less than? So then we kind of need to search through here and find the point with which there's 95% of the probability mass to the left of it. And then we get 0.02. So we're 95% confident that the probability of failure is less than 0.029, whatever. And that's what it looks like on the plot. So here's the point at which 95% of the probability mass is to the left of it. Well, let's say, okay, so we haven't found any probability of failure, or we haven't found any failures yet. So we think maybe the probability of failure is even lower than this. And we want to prove that it's even lower than this. What might we do to like improve our estimate? Yep, draw more samples. That's exactly right. So remember we had this 0.637 and 0.02. So now let's increase the number of samples to like 150. We still don't observe any failures. And so now we're actually 78% sure that it's less than 0.01, and we have the kind of the smaller number for our 95% confidence one. So I think there was kind of a question that came up last week or the week before of like, when do you stop, or how do you know if you're confident enough, that kind of thing. So this could potentially give you that kind of information. So the cool thing about Bayesian estimation, like I just said, is it kind of gives us a way to quantify the confidence in our estimates, which is a little bit more difficult to do with the maximum likelihood, although there are ways, and I think I have an exercise in the book about how we do that. But yeah, so we can do these very cool things like I showed in the notebook. Okay, so that was direct estimation. So again, we kind of have this issue with rare failure events where this isn't going to work so well. I'm going to use that idea to motivate this thing called importance sampling. So let's compare direct estimation and importance sampling. So for direct estimation, what we just did was we drew a bunch of samples from the nominal trajectory distribution, and then we estimated the probability of failure by just dividing the number of failure samples by the total number of samples that we saw. Okay, so what might be a problem with this method? This is a pretty rhetorical question because it just keeps coming up over and over again in this course, but it's going to be inefficient for systems with rare failure events. So you can imagine we were talking about, you know, if a system has a failure probability on the order of 10 to the minus 9, we might need a billion simulations just to observe one failure, but we're not going to feel super confident in our estimate of the probability of failure after just observing one failure. And so we're probably going to need even more than a billion simulations to actually estimate the probability of failure, and this can be extremely inefficient. And so that motivates the need for kind of another method, which is called importance sampling. And the key difference here is that instead of drawing samples from the nominal trajectory distribution, we're going to draw samples from this other distribution that we call a proposal distribution. So you can kind of make this connection here. This is similar to the proposal distribution for rejection sampling. That's more likely to produce failure trajectories. And then, so now we're actually probably hopefully going to observe some failures, which was our issue that we were having with these rare failure events. But if we were to just kind of take the average of that, like divide the number of failures we saw by the number of trajectories simulated, that's going to give us a completely wrong estimate of the probability of failure, because what's actually going to happen in the real world is we're going to see trajectories from this nominal trajectory distribution. But it turns out that it's possible to still get an estimate of the probability of failure using samples from this other distribution by re-weighting them. So let me show you what that looks like. Okay, so the first thing that we're going to do following these steps is we're going to draw samples from a proposal distribution that's more likely to produce failure trajectories. So you might have some ideas of how you might get that, but we're not going to talk about how we get it for now, but let's just say we have it, and we're going to call it Q. So we draw samples from this proposal distribution, and now we want to estimate the probability of failure. So here's what we're going to start with. We're going to start with just the definition I showed earlier for the probability of failure. So it's equal to the expectation when we draw trajectories from our nominal distribution of that indicator function of whether or not they're a failure. Okay, and then we also showed we could write this out as an integral where we take the nominal density and multiply it by this indicator function. Okay, and then now I'm going to do something that might seem a little bit weird at first, but I'm going to multiply this equation by 1, but the version of 1 that I'm going to choose is q of tau over q of tau. So essentially I'm just multiplying things by 1, but I've introduced q of tau into our formula now. And then we'll just write everything else as it was. And then now all I'm going to do is just switch the location of these, not those, of these. Just switch the location of the things that were there, just to make it easier to see what's about to happen. So this is still valid. All I did was switch the ordering of things. Okay, and so this might look a little bit like this equation, where the expectation, we take the density that we're sampling it from, multiply it by the thing that's inside the expectation. So this is actually equivalent to the expectation if we were to draw samples from Q of tau of what's in here. So of P of tau over Q of tau times this indicator. Okay. This is like one of the most like, yeah. Oh, can I? Yeah, can. Does that help?
Somewhat.
Yeah, okay. I'm also gonna, after this, show like a not handwritten version of it, so that should help as well. Okay. So yeah, I just derived kind of the fundamental idea behind importance sampling. So all we did, it might look a little weird, but we just multiplied by 1 and rearranged some stuff, and we found out that we could take an expectation over this other distribution instead of the nominal distribution that we were sampling from. And then to compute an expectation, you could just kind of take an average of a bunch of samples. And so you could imagine what we might want to do then is our estimate for p fail, so we'll call that p hat fail, is then just going to be equal to kind of an estimate of this expectation okay. And then I'm just going to rewrite this. I'm going to call this part WI, just to make it look more similar to what we had before. And this WI is just equal to our P tau I over Q tau I. Okay, so basically we just said we can take this expectation here and we can estimate it from a bunch of samples from Q of tau by just computing that average there. Yeah. P of tau is the nominal trajectory distribution, and Q of tau is the proposal distribution that we're sampling trajectories from instead. Yeah.
It's a tau I indicator, right? So it's the
Thanks. Oops. Okay, so let's look at this in slightly neater writing. Okay, so we said we're going to draw distributions from this proposal that we call Q. We derived this expectation, and we said one way we can estimate this expectation given samples from Q is to just kind of take an average of this value for all of our samples from Q. And then we just replaced this P over Q with this W. And the reason for that, okay, and then by the way, what's super cool about this is that this estimator is actually both an unbiased and consistent estimator of the true probability of failure, even though we didn't take distributions from the true like nominal distribution. So that's super cool. That's kind of the huge insight behind importance sampling. And just to kind of make a further comparison to show you that there's not too much craziness going on here, for direct estimation, we drew samples from P, we drew samples from the nominal distribution, and then we just estimated P fail by taking this kind of sum here. And then for importance sampling, we draw samples from a different distribution that we call Q, it's our proposal distribution, and we just estimate the probability of failure as kind of a weighted sum of whether or not it was a failure. So basically what we're saying is like, we can't just treat all of these samples as the same because they didn't come from our true distribution. We need to kind of re-weight them according to what they would look like in our true distribution in order to get an accurate estimate for the probability of failure. Yeah. You're on it today. Or I could put it over here. I just meant to write M times P fail. Okay, anyway. Also, there's no P fail over here. P hat. All right, I'm gonna stop trying to do this. All right, here we go. Any questions up to this point? Or other errors in my slides? Oh, a lot of hands went up after I said that. Yeah.
In reality, like, so much of your probability of failure will depend on your nominal, your choice of nominal trajectory. And so if I were to like the Corso example of like, people don't run into cars. With what probability? 0. Because I don't think that's true. I've been into New York City at 2 a.m. Okay, so like how do you really estimate what, things like what we talk about here about those points, like if your experience, if your traffic is inexperienced or experienced or in Venezuela or America, like the reality of the nominal distribution is much different. So like how do you think about that? Like it's not going to happen. It's never going to be true. It's
Yeah.
gonna be some like real, course
Yeah.
fitting of what happens in data.
Yeah, that's a fair question. So the question is like you're modeling P and then you're doing all this stuff to get an accurate estimate, but if P is not accurate, then the whole thing is not accurate and it's probably hard to get an accurate P. Totally true. So that's why modeling is so important. That'd be my first answer. There are a few things you could do. So you could do like a sensitivity analysis. So you could say like, if I got P wrong and I got it this amount wrong, like does my probability of failure change a lot? And if it doesn't, then you can be like, okay, well maybe I'm still like comfortable with these results. If it does, then you better double down and figure out P. Maybe I'll let Mykel speak to this more, but I know for collision avoidance, like what they did is they had like 9 months of radar data from the US airspace that they could use to model the behavior of aircraft. And so that allows you to get a pretty accurate model in that case, specifically. Yeah.
So this is still assuming that we have some failures. So it doesn't actually encourage us to see more failures at all.
Like in terms of sampling from Q? Oh, I did not.
Well, in either case, in either direct estimation or important sampling, we actually have to see some failures for either distribution, either values of distributions. Either values do.
So for when we do direct estimation, yeah, we need to see some failures from P. Otherwise, we're just going to get an estimate of 0. When we do this estimation, we need to see failures from Q. We're never going to sample from P in important sampling.
But we still have to see some failures.
Yep, you still have to see some failures from Q. But you're going to pick Q in a way, yeah. And we're going to talk pretty much for like the rest of this lecture and next lecture about ways to pick Q. Yeah.
So you just said maybe you get P a little bit wrong. Can you again be like Bayesian about this and have some PhD Bayesian and then you do this and you get again something like a beta distribution or something like that? Do people do that?
But that's exactly where my mind is like, if we increase the number of flight hours that a pilot has, then I would expect that their trajectory would get more safe to save the pilot, right? Versus if you just have the statutory 50, which is why no one gets a pilot license with just 50 hours, even though it's statutory, like it is legal. And so like if I'm modeling it now, well, my P of failure, given that other pilots will have at least 3,000 hours, well, that's going to be much safer, independent of anything else. So the best way to improve my P of, or reduce my P of fail is to, make my nominal trajectory safer.
Oh, sure. Yeah. Okay. So I think there's a lot to unpack there. But so one, yeah, if you want to actually change the P of fail of your system, you might need to consider design considerations. But that's kind of outside the scope of this class, particularly. I think what you're kind of describing, where a pilot that has more flight hours is maybe less likely to behave in a certain way than a pilot that has less training. That's kind of getting into this conditional idea. So you might want to say what is the probability of failure for an experienced pilot versus other, and that will change how you model P. I guess for when you gather 9 months of radar data from the airspace, the assumption is you're getting some data from pilots that are experienced, some that are inexperienced, and in the frequency that you would expect to observe in normal operation of the airspace. So you are kind of getting both. And then for the Bayesian question, yeah, you could do that. We're not going to talk about it too much. Yeah. Other questions here? Yeah.
Why is the nominal over the proposal 1?
Why? Back here?
Yeah.
Which step are we looking at?
So I think the third step, I can't.
here. Yeah, so I just switched like where P and Q are. Yeah. Yeah, just to make it look more like an expectation for the next step. Okay, any other questions on this? Yeah.
So just to be clear, we're assuming that we know both P and Q, is that right?
We are assuming that we know both P and Q, yes, but we only draw samples from Q. Okay, so oftentimes this weight here is called an importance weight, and the idea is that samples that are more likely under the nominal trajectory distribution, so this P tau I, will have a higher importance weight. So here's just what the algorithm looks like in code. I'm going to go through this kind of fast, but we draw samples from Q now instead of P. Then we just evaluate their PDFs to compute these importance weights, and then we return kind of, this is just a code implementation of this expression here. Okay, let's look at what this actually looks like. So here's kind of a cool graphic of this. Okay, so here's what's going on. There's a lot going on in this graphic, but let's look at just the direct estimation first. So here we're doing exactly what we were saying. So we were trying to estimate the probability of failure for this simple Gaussian system where it's a failure if it's in this red region, so below some threshold. So what we could do is just draw a bunch of samples from this distribution, take all the ones that are failures, divide that by the total number of samples, and we get an estimate for the probability of failure. So this is our direct estimation. And what I'm showing in this plot here is the number of samples on the x-axis, and then the y-axis is the absolute value of the estimation error. So because this is a small Gaussian system, we actually know the exact probability of failure. Typically we don't. So I can tell you what the exact error in our estimate of the probability of failure is. And then I run this 10 different times. I plot the mean error in the probability of failure and then kind of the spread of those errors. So ideally what we want to see in this plot is kind of a low spread where every time it seems to work pretty well. And then we want to have, low values such that our estimate of the probability of failure has a low amount of error. So ideally we want to be down here at 0. Okay, so you can see the direct estimate, it's got kind of this pretty big spread, it's got some error. And what we want to do with importance sampling is, given the same number of samples, so we drew 500 samples to get all the way to this point at the end, we want to see if we can get a better estimate of the probability of failure. And specifically, we want to sample more failures to do that. Kind of the more failures we sample with a few other conditions, the better estimate that we're going to get. So now let's imagine that so here over this side, I'm going to be showing the importance sampling distribution. So right now it exactly matches the nominal distribution, so it's the same thing as direct estimation. But now let's try to get an importance sampling distribution that will sample failures more often. So to do that, we can kind of move the mean of this distribution to the left here. And you can see already we're doing a lot better. So this blue line here shows the error of our importance sampling estimate and the spread. So you can see that the variance is much lower and the error is much lower. So we've done much better just by kind of biasing the distribution we sample to be able to sample more failures. There's another way to look at this that people often look at called effective sample size. If this doesn't resonate with you or doesn't make any sense, you can forget about it, but I think it's one useful way to look at things. And the idea is the effective sample size. So when you're doing direct estimation, the effective sample size is just the number of failures that you observe. So here I think it's 13 or something like that, so it's this gray region here. Now here we've moved our distribution over and we've observed actually this many failures, so what this line shows here. But that's not our effective sample size because we observed these failures, but we observed them under a different distribution. So they're not necessarily weighted the correct way under the distribution we expect to see. So our effective sample size is actually lower than the number of failures that we observed because they're not kind of all equally weighted according to this nominal distribution we expect to see. Yeah.
That's probably a stupid question, but all of these estimation schemes gives us a single value, right?
Yes.
How do we get a distribution out of that?
I did it 10 times.
Oh,
Yeah.
cool.
So the idea is like, eventually we'll do it like once if we have good confidence that like it'll always give us a good estimate. But clearly if I did it 10 times here and I got this whole spread of different estimates,
Right.
we can't be so sure that like when we do it on the real thing that we're gonna get something good. So that's why we want this low variance, because we wanna, when we eventually do it, we're gonna wanna do it once and we're gonna wanna trust that value that we get out.
And but you did it 10 times, it means that there was like 5,000 samples.
500, so over here 500, over here like 100.
Various number.
Yeah, various number of samples for that 10, all those 10
And
times.
then that 10 times.
Yes, 100 samples 10 times, 500 samples 10 times, and so on. Yeah. Yeah. Yeah.
And the secret that's being plotted is negative X.
I think I actually did like 5% to 95% confidence or something like that. Yeah, I'd have to look at the code. Okay, so the idea here is like we want to make our effective sample size as high as possible. We want to get as many failures as we can. And so to do that, we kind of want to sample more failures. So let's see what happens if we kind of keep decreasing this mean here. So now we're kind of centered at this failure threshold, so we're sampling a lot of failures. Our effective sample size has gone up a little bit. We're getting a little bit better. Maybe you could imagine we also decrease the variance here so that we sample more things that are likely failures. And now we're doing like super, super well because we're kind of sampling a lot of likely failures. Our effective sample size is pretty high. But this can go wrong. So you could imagine like if we did this and we weren't sampling many failures at all, like this is a really bad proposal distribution. We wouldn't want to pick this. But we could also pick a proposal distribution that samples failures but also does really badly. And that's because it samples a bunch of unlikely failures. So we both want to pick a proposal that samples failures but also samples likely failures more often than it samples unlikely failures anyway. So questions on this before I close this graphic? Yeah.
So actually important sampling has no knobs to fill at all except for the stuff from the last lecture, which is how do we find failures. Is that correct?
The main knob you can turn in important sampling is the number of samples and the proposal distribution that you pick.
Yeah, and the proposal distribution is basically last lecture. Like how do you find failures in the first place?
It's really the rest of last 9 minutes of this lecture and Thursday's lecture. We're going to talk about how to find it.
Okay.
Yeah. But I think what I'm about to show will like clear it up a little bit. Okay. So what I was kind of trying to show there is that we want a proposal distribution that samples likely failures more often than unlikely failures. And so that might get you thinking like, is there an optimal proposal distribution we can pick? And so let's think about for a second what that might be. So we're going to define the optimal proposal distribution. So we have to say what we mean by optimal. We're going to say it's the one that minimizes the variance of the estimator. So here's the variance. I'm not saying that you should know how to derive this, but here's what the variance of the importance sampling estimator looks like. And we want to see if we can kind of minimize this variance. So I'm just going to give you a proposal distribution to try out because I already know the answer. Let's see here. Okay. So let's try Q of tau is equal to P of tau times this indicator function over P fail. Okay, so what I'm going to do is, yeah.
What if I gave you a proposal distribution that samples 0 failures whatsoever? Like I guarantee you it's like way outside of the scope of any possible failure. Isn't that also minimizing the variance of the estimate? P fail is 0.
P fail is 0.
Like I gave you a proposal to say what our failure region is, like somewhere on the left. I gave you a proposal distribution that's like no variance whatsoever in my proposal distribution. It's all the way to the right.
Yeah, I think it would minimize the variance of your estimator because you're always going to get an estimate of 0. So variance isn't maybe the only thing we want to look at because like it will minimize the variance. You'll always get an estimate of 0.
Like I guess then.
But like that's not very useful.
Is this our definition?
Because this one won't always give us an estimate of 0.
Oh wait, but we defined optimal proposal distribution as well.
Yeah, so there's multiple that will minimize this variance.
Oh, I see.
Yeah, we should pick the one that's like useful to us. That one's not going to be useful. Yeah. Okay, so here it turns out, like, spoiler alert, this is the one that's going to be useful to us. And so you could imagine that if I go ahead and plug this in to our formula for the variance, we're going to get, this expectation, P of tau, minus, and so we're going to plug in for this Q of tau, we're going to plug in this thing here. So that's going to be P of tau times P fail. Sorry, this is getting kind of messy. All of this over Q of tau. Okay, and so if we look here, stuff's going to cancel out. So this P fail is going to cancel out with this one. And then we have this minus this, which is the same thing. And so as you might have been guessing, we're going to get 0. So the lowest we can make the variance is 0. So the proposal that minimizes this variance is going to be this one here. Let me just make this easier to see. Okay, so we basically just showed that the optimal proposal distribution is equal to this distribution here. Does this distribution look familiar to anyone? Yeah. Yep, exactly right. It's the failure distribution. But, as you just mentioned, it's written in terms of the normalizing constant, which we said was p-fail, which is the thing that we're trying to estimate. So we have a problem here where we want to estimate p-fail, and I just told you the optimal distribution that we should sample from if we want to estimate p-fail is this, but we don't know p-fail, so then we don't get to know this distribution. Okay. So the best thing that we can do now is just kind of do our best to select a proposal that is as close as possible to the failure distribution. So when we select our proposal, this is what we have in mind. We want to get as close as we can to the failure distribution. If we knew the failure distribution, we wouldn't be doing this whole thing in the first place. And like one note here that's kind of important to think about is when we select the proposal, we need to both be able to draw samples from it, and we need to be able to compute the normalized density. So we could draw samples from our failure distribution. We talked about how to do that last lecture, but we were just saying we don't know how to compute the normalized density for it. So that's why we can't do that. Okay. So one thing that we might do, so like we just said from previous lecture, we know how to sample from the failure distribution, but we don't know how to compute its normalized density. And so what we might want to do is we could try to fit a distribution that we know how to compute the normalized density for using samples from the failure distribution. So for example, we get a bunch of samples from the failure distribution, and then maybe we take those samples and we fit like a Gaussian distribution to them because we know the density of a Gaussian distribution and we know how to draw samples from it. Okay, so I think we have just enough time before we wrap up for me to show you this Pluto notebook, and then we'll have to pick up where we left off next lecture. Okay, so what's going on here is we draw samples from our failure distribution. We can do that using any method that we talked about from the previous lecture for drawing samples. So here I'm using MCMC sampling to draw samples from our simple Gaussian distribution. And then all I do is call fit on those samples, and I fit a new distribution, a normal distribution to those samples. And use that as our new proposal. So you can see like the true failure distribution is that red thing there. The distribution that we fit is the one that's got all the samples on top of it. And you can see that that ends up doing pretty well compared to direct estimation. So we fit a pretty good proposal doing this. Yeah, are there any questions on this? Yeah.
Actually, I understood it, I guess, wrong before. I thought that when you say we sample from Q, it's actually the process that we discussed in the last lecture where we like find failures, where we also kind of sample somehow or generate failure examples. And I thought this was exactly sampling from Q, but this is actually not the case. And you're saying this finding failures like we did in last lecture, we cannot, I guess, compute the probability of the samples, and this is why we can't use it to reweight our samples?
Yeah, that's exactly right. So the key thing that I mentioned with Q is we need to be able to sample from it, but we also need to be able to compute the normalized density of it so that we can compute those importance weights And so because we could only draw samples in the last lecture and we couldn't compute the normalized density, and in fact, in computing that, it requires us to know the probability of failure, we can't use that as our distribution.
See, I mean, I don't know, intuitively it seems to me that somehow you could, in like rejection sampling or something, quantify the probability of any given sample coming out of rejection sampling. But maybe it's, so which would, I guess, satisfy this, but maybe it's not possible, I don't know.
Yeah, there are. So if you could sample from the failure distribution, your importance weights would be exactly equal to the probability of failure, and you have zero variance. I think it's one of those things you kind of have to just think about.
Yeah,
for a while.
I'll do that.
Yeah. Yeah.
I think last week we said that the proposal distribution for like the other sampling methods have to be larger than our actual distribution. Is this the case here as well, or not necessarily?
It is not. So we said it had to bound the failure distribution. I need to double check, but I think it's just the supports need to overlap. So you need to make sure you're assigning non-zero probability in your proposal distribution to places where your other distribution also assigns non-zero probability. Yeah.
Wait, what exactly are you fitting? Because we can get a bunch of samples from the failure distribution and do a bunch of counts. What are we fitting to make you fail?
Any model class we think is a good idea. So in this case, I just fit a Gaussian distribution to the samples.
Wait, sorry. The how does a series of failures I hand you tell you anything about the probability of failure? Like, say I had a just excellent failure detector, and I'll give you a bunch of failures.
I'm fitting to samples from the failure distribution. So that should tell me what the failure distribution is like.
Oh, I see what you mean. Okay, great. Thanks.
Yeah. Okay, I think we probably need to wrap up there because we're over time. But we'll pick up with this on Thursday.